All right, good morning, everybody. I'm really excited because I have my new webcam today. And the webcam obviously is doing a better job of capturing clarity and picture on the board. So now you should be able to see everything very nicely during class if you have to watch this online. So for instance, Clarissa missed class the other day. And so I wanted to remind her and all of you how easy it is to find these videos. Hi there, Rose. If you go to our class page, and you go to announcements, then one of my announcements is in all caps. It says all videos of our class. So you click on that link. Well, not a link, but you click on it, and then it gives you a YouTube link, and you copy and paste that YouTube link, and here is a list of all the videos I've made thus far. So we have the last 5 videos, or the last 5 classes on here, and I'm now recording today's class with the webcam, and the video quality will be even better. So if you miss class, you can go back and watch it, or if you just want to watch it again, you can go back and watch it again. Okay, so glad to see everyone brought their blankets. Rose, here's your practice test from before. Okay, so folks, over the weekend, I was just going through and solving all the problems in the book and in Math AS, you know, just making sure I was familiar with everything that was coming up. And over and over, thematically, we just keep coming up against the idea of using the function, the derivative, and the second derivative to find the maximums, the minimums, and checking concavity to see if it's concave up or concave down, and seeing what the value, how high up and how low it is. So as we work through today, I want us to constantly be thinking about how do I use the function, the derivative, and the second derivative to find all this information. So just as a review, I know that we've already done this screen before, but how do you find the x-intercepts? How do you find the max min? And how do you find the point of inflection? How do we use all this information? So for instance, the function itself, if you solve f of x equals 0, what are you finding? If you set the actual function equal to 0, what is it that you're finding? That's a good idea. Let's start there. F of x itself is the y-coordinate. That's a good point. F of x is the y-coordinate, okay? So when you actually plug a value into f of x, that's telling you where that coordinate is actually high or low. Where is the coordinate on the graph? But what do you solve if you actually set f of x equal to 0? What is that telling you the y-coordinate is? 0. And that means that y-coordinate is on the x-axis, which means you just found a x-intercept. Yeah. So when you set f of x equal to 0, you find x-intercepts. Okay. So that's very important. That's how we use f of x. Those are the 2 ways we use f of x. F of x is telling you the y-coordinate, and if that y-coordinate happens to be 0, then you just found an x-intercept. So then how do we use f prime of x? What is that telling us? That's telling us the slope. It's telling us the slope. And if you set f prime of x equal to 0, what did you just find? A what? Not an inflection point. A critical point, right? So if you set it equal to 0, you just found a critical point. Now that critical point, I'm going to summarize them here. A critical point could be what? It's anywhere the slope suddenly turns 0. So it could be a max, it could be a min, or it could be a, it could be that. It could be a changeover point. And notice in particular, what is a changeover point? It's also a inflection point. So a critical point could be an inflection point. It might not be. These are not critical inflection points at all. It's the same concavity throughout. But here, that's an inflection point, so that's a changeover point. And or your critical point could just be a flat line. Okay, very good. So, but you don't know yet. You don't know which of those things it is until you calculate what? The second derivative. Yeah. And once you calculate the second derivative, if the second derivative is negative, then it's concave down, so it's a maximum. And if the second derivative is positive, then it's concave up, and it's a minimum. If the second derivative is 0, well, you don't know yet. It could be a changeover point. It could be just a flat function. Now, we don't just set f prime of x equal to 0. What else do we set it equal to? This is kind of weird. You don't really set it equal to it. But you wonder, when is the first derivative 0 and when is the first derivative
Undefined.
Undefined. Yeah, when is it undefined? Because what might that look like? If the first derivative is undefined, remember that means there's no well-defined tangent line. So it could be a cusp. It could be a teeter-totter point, like that. It could be a funky-looking cusp like that. What else could it be? It could be an asymptote. I'm going to write asymptote. And or what else could it be? If the derivative is undefined, it could simply be a pole. Right? So there's a lot of different things that it could be if the first derivative is undefined. Now, if the first derivative is undefined, can you calculate a second derivative? No. If the first derivative is undefined, you can't then calculate a second derivative. So there's no second derivative test to find out what these things are. The second derivative would also be undefined, because if the first derivative is already undefined, you can't very well calculate a slope of something that's undefined. So we don't, you would have to, how would you know which one of these you're looking at? You'd have to graph it. You'd have to graph it. Okay, so that's how we use the first derivative. So then how do we use the second derivative? What does it mean? The second derivative is the... What does second derivative tell us? Concavity. It tells us the concavity. And again, in my head, I always think about this notion of a circus person who bends metal bars, to entertain the audience. Concavity, if you just have a regular metal bar, that's zero concavity. But if you bend it one way or the other, that's concavity. So the second derivative tells you concavity. And when we set the second derivative equal to 0, what do you find? Rose already said it. The inflection point. Yeah. So you have to put all of these together in any situation to understand what you're looking at in a function. Now, again, there's a certain irony here, because if you really were wondering what a function looked like, what would you really do? You would just graph it. But the fact of a calculus class is that you're learning calculus so that you could analyze a function if you didn't have a graphing calculator. I know that that is a huge irony. You're like, well, why couldn't I just graph it? I'll just graph it. I mean, obviously, that's the best way to find a max or a min or what all those things look like. But the thing is, if you don't know how to do any of this stuff and you just use a graphing calculator, later on there will be problems that are harder than all of this that you can't do by graphing. And so you need to have all these tools under your tool belt in order to do those harder problems later on. So that's always the reason why you learn things, when it doesn't look like there's a reason to learn things. Like, isn't that the classic thing in mathematics? Why do I need to learn this? I could just do this, or I could just do that. But it's always for later on. Okay, so today we're going to wrap up section 2.8 because there are a few problems that we didn't do. And then we'll do section 2.9. And I put all that over there on the table. Did everyone grab a packet of 2.9 and sign in? Okay. Did I already tell you? Oh, no, I didn't tell you this joke yet. How does NASA organize a party? How does NASA organize a party? They plan it. Yeah, okay, all right. So here we go. Julie asked, oh no, this isn't what I wanted. Julie asked that we take a look at number 2. And I'm perfectly fine with us looking at number 2. Now, first of all, did we solve number 2?
No.
Or did we skip it because we had already done one like it?
Skip it.
Okay, well, it's not a terrible thing for us to go ahead and look at it because I want to talk about this process. Because this is the process. This is what you're doing for the whole rest of this course, essentially, is playing these 3 facts against each other. So in number 2, when they want us to look at the function f of x equals x squared e to the what? 14x? They say for this function there are 3 important intervals where a and b are critical numbers. So right up front they're telling us that there's 2 critical numbers. That means there's 2 values when the derivative is equal to 0. Could the derivative ever be undefined? Could this derivative be undefined? No, because to be undefined, what do you need in the formula? You need a what?
Divide by 0.
Yeah, you'd have to divide by 0 or square root a negative. But there are no square roots and there are no fractions. So we're not going to be undefined. So therefore, the 2 critical values we're looking for is when the derivative is equal to 0. Okay, And then all it says at that point is for the following intervals, tell whether it's increasing or decreasing. We're going to do the whole thing. We're going to do the whole thing and really get an idea of what this function looks like, because this is one of your test problems. Okay? So like, definitely do this problem with me, put a star on it, say, this is a test problem. So I'm walking you through the entire problem that you will see on your test. Okay, now for kicks, what would probably be the first thing you'd want to do for a graph like this, or for a function? Probably graph it, just to see what it looks like, right? Now, when you're taking the test and you're looking at your graphing calculator on your calculator, unfortunately, a graph like this is very, remember, it's really flat. You have to zoom in quite a bit to even see what it looks like. So you might just want to keep in mind what this looks like. E to the 14x, did I do that? Yeah. Okay, so keep in mind, when you're looking at this function, look how terribly flat it looks. Doesn't it just look like it goes straight to the right and then up? That's all it looks like. But what's really happening, if we zoom in close here, you still can't even see what's happening, but I'm going to change the y value to go from negative 0.01 to positive 0.05. Ah, now what is the function doing? So I want everyone to draw that right up front. Let's go ahead and draw this. The activity is to the left of the y-axis. And what's happening is that you have this long buildup from the left where it's swooping up. So what's the concavity there? For this part of the graph? Concave up. So here we have concave up. And then at some point, it rounds back down to head back down towards the x-axis. And there's our concave down portion. And then it swoops back up and heads up to infinity and forever. So there it's once again concave up. So seeing as how this problem shows up over and over in the book and online, then I'm going to put it on the test. This would be just a good thing to memorize, that this is what this function looks like. Do you know why it looks like that? This reminds me of a Dr. Seuss book, The Vug Under the Rug. It's this scary scene in There's a Was It in My Closet, where there's a bug under the rug and it's really scary. The room is dark and you just see this object underneath the rug. It always scared me as a child. Well, I want you to imagine, what are the two graphs here? What's this first part of the graph? What's the x squared? It's a parabola. So just imagine, if I were to go ahead and graph a parabola, but then what's the second part of the graph? E to the something. It's just an exponential curve. And an exponential curve looks like this. And so if you add those two functions together, if you literally overlapped them, well, the parabola part over here would push up on this part of the exponential curve, and you'd get this little bloop before it continues that way. So this is actually exactly what we would expect if you overlay a parabola on top of an exponential curve. Over here, the parabola and the exponential curve are both going in the same direction, and so that's why that part of the graph is going to the right. But over here, the parabola has just enough oomph to push up a little bit on the exponential tail, but then overall, the exponential tail is so much shorter than the parabola is tall, and the exponential tail wins. So I don't know if my little description just made sense there, but can you, just by looking at this, can you see the exponential curve? And can you see the parabola? So it really is two functions overlapping on top of each other, merging together into one, as if through marriage or some sort of union. Okay, well, now that we know what the graph looks like and we know what to expect, let's go ahead and do all the work. So what do we do first? First, we do the first derivative. They even start with the same word. First, do the first derivative. So we're going to do the product rule. So the derivative of the first times the second plus the derivative of the second. And maybe now you've memorized that when you take the derivative of the e to the something, it's going to be that number comes out front. E to the 14x times the derivative of 14x, which is 14, times the first. There we go. So we did the derivative of the first times the second plus the derivative of the second times the first. How do we clean that expression up? Yeah, you pull out the e to the x term. So I'm going to pull out e to the 14x up front, leaving behind 2x plus 14x squared. How does everyone feel about that part so far? Okay, well, so looking again, we know that the first derivative is telling us the slope. And what's interesting is to find when the slope is 0 or undefined. It's not going to be undefined because we're not square rooting or dividing, but it could be 0. And again, looking, an exponential function is never 0. So this term will never be 0. But this is a parabola, and it could be 0. So what we need to do now is set this thing equal to 0. Set the derivative equal to 0. This part will never be 0. And effectively, we get rid of it by dividing it off. We move the e to the 14x over to the other side. And what happens to it? It goes to 0. And that's why it doesn't matter. So we have 14x squared plus 2x equals 0. And how do we solve for x? Yeah, you would just factor. So I can factor into 2x. And that's what, 7x plus 1. And that should equal 0. So both of those, since 2x times 7x plus 1 equals 0, either or both of them will equal 0. So 2x equals 0, or 7x plus 1 equals 0. And therefore, x equals 0, or x equals negative 1/7. And is that, in fact, where our critical values were? We did, in fact, have a critical value at 0. That was correct. And sure, that could be 1/7. That could be negative 1/7, the location of our other maximum. Okay, so what do we do next? At this point, we're looking at the graph, so we know that that's a minimum and that's a maximum. But yes, Nate?
Sorry. So those are the critical values? Or?
Those are the critical values. These are the critical values because they are when the first derivative is equal to 0. Yeah, the critical points are when the first derivative is equal to 0. Yeah. Now, there's going to be two things that we do with this, folks. We're going to find the second derivative to find out if these points are concave up or concave down. But we're also going to plug them into the first function, the actual function, just to find out how high up and how low down they are. So we're doing both. You always start your problems by doing the first derivative to find your critical points. And then you're going to plug it in to the second derivative to find out if it's concave up or down. And then you're going to plug it into the first derivative to find out actually how high or how low those points are. And honestly, you could do that in any order you like. But well, let's go ahead and keep going to the second derivative. And so now we get to do the product rule all over again. So we had e to the 14x times 2x plus 14x squared. This is a test question because it's such a significant computation. It really requires that you practice and be good at it. So the product rule, I'm going to erase that real quick. You do the derivative of the first, which is 14 e to the 14x, times the second, plus the derivative of the second, which is just 2 plus 28x, times the first. Does everyone feel comfortable seeing why the derivative of e to the 14x is just 14 e to the 14x? Just pulling that number down in front? Because that should be fairly automatic for you. If you're not sure about it yet, you take the derivative of the outside function, which is e to the something, and that's just e to the something. And then you multiply by the derivative of the inside function. The inside function is 14x, and the derivative of 14x is 14. But instead of putting 14 after, you put it in front. Okay, so now how do we clean this up? Pull out the e. So we have e to the 14x. And I'm going to put some big brackets here. That still leaves me with 14 times 2x plus 14x squared, plus 2 plus 28x, with the e to the x out in front of all that. We do want to clean this up. E to the 14x times what? 14 times 14 is 196x squared, plus 28x, plus 28x, plus 2. Which is e to the 14x, 196x squared, plus 56x, plus 2. right now, what really matters is what is the question asking for? This particular question, they just wanted to know when is the graph increasing and when is it decreasing. And to do that, we just need to know, are these points maximums or minimums? And so we can go ahead and just plug our critical values into the second derivative just to find out if it's positive or negative, concave up or concave down. And I'm completely out of board space. Do we have to set the second derivative equal to 0? What would we be finding if we set the second derivative equal to 0? We'd be finding the inflection point. Where are the inflection points on this?
Between concave up and concave down.
Yeah, you've got one right there, right? But when it switches from concave up to concave down. And then we have another one here when it switches from concave down to concave up. This problem isn't asking us to solve for an inflection point. But if it did, that's what you would do next. You would set this equal to 0 and find out where the inflection points are. And then you could say where it's concave up, where it's concave down, and where it's concave up. We won't do that right now, but if you did need to, you would set that equal to 0, which really means what would you set equal to 0? Yeah, just the quadratic part. You would just do the quadratic part, and you'd solve the quadratic formula, or you'd factor it, but no, probably the quadratic formula, and you'd get your answer. For right now, all we wanted to know was how high up, or no, was it concave up or concave down? So what happens if I plug 0 into all this? Yeah, this would be pretty simple to calculate. The second derivative at 0 is e to the 0 times 0 plus 0 plus 2. And what's e to the 0? 1. So 1 times 2 is 2. And that's positive, so that's concave up. Right? So f of 0 should be concave up, and it obviously is.
2 years ago, I guess, when it started, she said, I'm going to ask you some questions, and don't shoot the messenger.
Okay, so what about plugging in -1/7? -1/7. Now let's see here. I'm going to erase some of my previous work, folks, so I can actually do that computation. So when I plug in -1/7, the second derivative evaluated at -1/7. This is the work you'd have to show me, by the way. You'd have to actually show me plugging the critical number into the second derivative and proving to me that it's concave up. So if I plug in -1/7, that's e to the 14 times -1/7. All times 196 times -1/7 squared. And then plus 56 times -1/7. And then plus 2. Now what's probably the easiest way to do that computation, folks? Yeah, just plug it all into your calculator. I mean, we can do some of it. This is e to the -2. And then I have, whatever that is. Well, I can actually just do it. It's 196/49. And then that's -8, and then plus 2. Actually, I could probably finish doing this in my head. E to the -2 means 1 over e squared. That's a positive quantity. 196 divided by 49 is roughly 2, right? If that's $2 and that's 50 cents, $2 divided by 50 cents is 4. So that's 4 minus 8 plus 2. You know, even just doing this, you know, roughly, approximately, 4 minus 8 is -4 plus 2 is a -2. This turns out to be a negative number. Even if I don't finish the computation, you know, doing it exactly, I know that a positive times a -2 is going to be a negative. And therefore, this is concave down. Now, obviously, you can just plug it into your calculator and you'll get the actual value. But when you're doing the second derivative, what's all that matters? Is the answer positive or negative? The actual value isn't critical. It's not critical. All right, well, that told us that this indeed, since it was concave down, that makes it a maximum. And since this was concave up, it was a minimum. And I think we finished our analysis. That's what our overall graph looks like. Now, what was the actual question? It says, on the following intervals, tell me if it's increasing or decreasing. So now, what is A in this problem? They asked us to solve for the critical values A and B. And since A is the first critical value from -infinity, what's A? Not 0.
-1/7.
-1/7. Because if we look at this number line, they're saying that the number line The number line goes from A to B. So it would be from negative infinity to A is our first, that's our first, chunk. And then from A to B is our second chunk. And then from B to infinity is our next chunk. So that's very important too, that you all understand which is A and which is B. They're saying important intervals where A and B are critical numbers. So you'd put A and B in order. And so A is negative a seventh and B is 0. Does that make sense? Okay. There was a bug on the board. And I think he was already dead. And he just disintegrated in my fingers. How sad. Nate?
So when would we plug it back in, or what would we find if we plugged it back into the original?
Okay, great, thank you. I still wanted to do that. So we have our critical values. We know that now that they're concave up and concave down, so they're maxes and mins. So now we plug it back into the original function, and that tells us actually how high up it is and how low down it is. That's the actual coordinate. So now if we plug into the actual function, so first of all, if we plug in 0, that's easy. Because what do we get if we plug in 0? We get 0 squared times e to the 14 times 0, which is just 0. So that tells us that at the critical value 0, the height is 0. Well, that's obvious because we saw that on our graph. So that tells us that this function actually goes through the origin. Whereas if we plug in negative a seventh into the function, that's going to tell us how high up the function is at that critical value. So very important that you plug that back in. It's negative 1/7 squared times e to the 14 times negative 7. So that's 1/49 times e to the negative 2. That actually cleans up pretty nicely because that's 1/49 times 1/e squared. And so your final answer is 1/49e squared. That's how high up that point is. So if you were to mark it on your y-axis, you'd say, okay, how high up is that point? That coordinate is at 1/49e squared. That's how high up it is, which is not very high, is it? I mean, that's a very, very, very small fraction. Okay, well, that's the problem, folks. What questions would you like to ask about this whole process? What was the flow? What did we do? Like, if you wanted to write out the steps, what was the flow?
We did everything that is up there.
Yeah, we did everything that was up here, but what did we do first?
We did the derivative, the critical points. We just did the inflection point.
Yeah, we didn't actually solve the critical point, but we started by doing the critical value. That was step 1. And then we did the concavity to tell us if it was a min or a max. Yeah, and then we went back to find out actually how high or how low it is. That's kind of ironic, isn't it? That the last thing we would do is actually evaluate the function. But of course, how did we know what to plug into the function until we found out what the critical numbers were? So definitely the first derivative is always your first step. And the second derivative is your second step. And then the actual function itself is just finishing the problem by saying where those actual coordinates are. How would you express those values as a coordinate? You would actually just write down the coordinate. Like this coordinate right here would be 0, 0. And what's this coordinate right up here? That's the coordinate negative a seventh, comma, 1/49e squared. Right? That's what it would look like if you actually wrote down the coordinate of the maximum. Okay, well.
Why we need to find out how high is it?
Well, like if you were actually doing a problem with money, like looking at profit or cost or revenue, you'd want to find the maximum profit and actually find out what that profit is.
But what if on the test, do we have to find out how high is it? No, right?
On the test, you should follow the instructions and do whatever the instructions say.
But for this instruction, it did not say find how high.
You are correct. I was just kind of walking us through the whole process.
Okay.
Yeah. Okay. Julie, does that answer your question?
Yeah.
Okay, good. That's a really good problem, folks. It'll definitely be on the test. So let's see. Today we had left off last time looking at number 12. Now, I don't think we'll do all of these because we just walked our way through the whole process right now. That's the whole process. This is what you would do on any given problem. You'd walk your way through all those steps. So in this particular problem, number 12, they're saying here's your function, and they're saying it only has one critical value. So you would find the first derivative, set it equal to 0, find your critical value. And then they're saying for x less than a, where a is the critical value, what does that mean? I think so. What does that mean for x less than a? Yeah, everything to the left. Exactly right. Everything to the left. If you look to the left of the critical value, what's happening? You said 2.8? Yeah.
You're lucky.
Yeah, and then when it says when x is greater than a, that means to the right of it. Is it increasing or decreasing? Well, how would you find out? I mean, let's just do this real quick. So for number 12, it says that our function is 5 plus 3x to the 6th. So we take our first derivative, and that's 6, 5 plus 3x to the 5th times the derivative of the inside, which is just 3. So we could certainly clean that up a little bit. The first derivative is just 18, 5 plus 3x to the 5th. And we would like to know when is that equal to 0. So we set it equal to 0. And you can immediately divide the 18 off, so that's gone. And then we have 5 plus 3x to the 5th. What's our next step for solving for x? How do you get rid of a 5th power? Normally, if something is being squared, you square root it. If something is being cubed, you cube root it. So you take the 5th root. So you take the 5th root of both sides. What's the 5th root of 0? Still just 0. You know, what can you multiply times itself 5 times to get 0? 0. All right, and then you move the 5 over, and you divide off by 3. And we get that our critical value is at negative 5/3. Well, okay, so that's our critical value. And if we actually look on a graph, here's negative 5/3. And we know that the slope at that point is 0. But what's actually happening on the graph to the right or left? Maybe we can all guess. What does essentially this function look like? It's something to the power of 6. Anything to an even power, like something squared, is a parabola. And something to the 4th power is a parabola. Something to the 6th power is a parabola. Anything to an even power is a parabola. So what does our graph actually look like? Some sort of parabola. So now that's kind of cheating to just go ahead and say, well, what's happening to the left of it? The function's decreasing. And what's happening to the right of it? The function's increasing. How do we actually find out? You could plug it in. What happens if I plug in negative 5/3 into the function? What do we get if we plug it into the function? F of negative 5/3 is 5 plus 3 times negative 5/3 to the 6th. But 3 times negative 5/3 is just negative 5. 5 minus 5 is 0. 0 to the 6 is 0. So actually that tells us that the parabola starts here. Looks like that. How do we know if it's, you know, if it looks like that or if it looks like this? Oh, you could always just plug in a point, I guess. Is that what you're saying? Plug in a point and see where it is?
If you're trying to see that you have to do the second.
Well, yeah, or you could just do the second derivative, because the second derivative is going to tell if it's concave up, and if it's concave up, you automatically know it's increasing to the right and decreasing to the left. So you would just take the second derivative. So the second derivative would be 5 times 18, which is what, 90, times 5 plus 3x to the 4th, and times the derivative of the inside, which is 3. So the second derivative is 270 times 5 plus 3x to the 4th. And what point do we plug in?
The negative 5/3.
Yeah, our critical value. So if we plug in negative 5/3, the second derivative, you plug in the negative 5/3. That'd be 270. 5 plus 3 times negative 5/3. Once again, the 3's cancel out. 5 minus 5 is 0. 0 to the 4th is 0. 0 times 270 is 0. Oh, darn it. Wait a minute. Did that really just happen? Did we get the second derivative as 0? Did we really? Did we make a mistake somewhere? Could it really be flat at the bottom?
90 times 4
Uh-huh.
is 360.
Right, but you have to first plug in -5/3, right? And when you plug in -5/3, 5 minus 5 is 0, and 0 to the 4th is 0, and 0 times 270 is 0. What does our graph look like, folks? This was 5 plus 3x to the 6th. Oh, 5 plus 3x to the 6th. Whoa, look at it. Is it flat at the bottom? This is pretty interesting. Could the concavity be 0 at the bottom? It's possible. That seems to imply that it's actually flat down at the bottom. I find this very hard to believe. I don't know what just happened. You would think that this whole thing is concave up, because otherwise that implies that it's flat at the bottom. It's 5 plus 3x to the 6. You do the derivative of the outside, leaving the inside alone. And that was that. And we set it equal to 0. You divide that off. And that's -5 divided by 3, -5/3. But then apparently when you plug it back in, folks, is the answer key on this one? Well, we know it's decreasing and increasing. We certainly know that just by graphing, and you're all free to graph it to confirm. But that's awfully strange that the concavity turned out to be 0. I'm a little perplexed by that one myself, because I would think that the concavity at the bottom would still be concave up.
I had a similar one in that.
Really?
And they did the same thing to me, and I was like, I don't know.
Yeah, this is very surprising. I don't think that I've ever come across such a problem like that before, because that implies that it's flat at the bottom. Because if concavity is 0, that means it's flat. It's not concave up or down. But that is just truly shocking. Well, I don't want to say, well, that's okay, just look at the graph. I think what you can do, and maybe this is what Nate was saying, if you choose a point to the left of -5/3, like what's a point to the left of -5/3? That's -1.666, right? What if you chose a point to the left, -2, and it chose a point to the right at -1? And then you just check the slope at that point. You could check the slope at that point. That would be another way of verifying that it's increasing or decreasing. Nate, is that what you were saying originally? Yeah, you could totally do that. So in our case, the first derivative, everyone do this with me and just try it out, see what it's like. The first derivative is 18, 5 plus 3x to the 5th. And so we're saying, what's the slope just to the left of our critical value at -2? Then that would be 3 times -2 is, so that's 5 minus 6 to the 5th. That's 18 times -1 to the 5th. And -1 to the 5th is -1, so 18 times -1 is -18, which means it's decreasing. Folks, my message to you is that concavity thing didn't work out. And I'm not sure why it didn't work out. I'm pretty shocked. Normally that would have worked. But the question is, how do you demonstrate to your audience that something really is happening? You know, it's not enough to just say, look at the graph. It's clearly decreasing and increasing. The purpose of the class is to demonstrate through numbers and figures and equations, how do you demonstrate that something is actually the case? Like if you were a lawyer in a courtroom, how would you actually make an argument that it really is decreasing? And we just did that. We now have an argument that states that to the left of our critical point, the slope really is decreasing. And then if they said, okay, well now prove it to me that it's increasing to the right, you'd say, well, I'll choose a point to the right and prove to you that it really is increasing. So you would plug in a value to the right, and then 3 times -1 is -3, so 5 minus 3 is 2. And 2 to the 5th is 2, 4, 8, 16, 32 times 18 is a large number. And it's positive. So therefore, it's increasing. So the question is, how can you make arguments using mathematics? How do you build arguments? How could you convince a jury? How could you convince an audience that something really is so, where the #1 rule is you're not allowed to just point at a graph? And so we have 2 different ways to do that now. You could, in most situations, just calculate the second derivative and look at the concavity, and that would tell you it's increasing to the one side and decreasing on the other side. But if that concavity test fails for some reason, you could still just calculate the derivative a little bit to the left and the derivative a little bit to the right, and then you can still show it's decreasing or increasing. Does that make sense? Nate?
So say that it did work out, the concavity. So if it was negative, that would tell us it's
Increasing to the left
okay.
and decreasing to the right. Yeah. Okay, well, I'm kind of glad that that second derivative test failed, because that shows that we actually do have a backup argument. The backup argument is to simply calculate the derivative to the left and right of your critical point, and that will tell you if it's decreasing or increasing. So how would you write your final answer for this one? You would say, you know, to the left, it's decreasing, and to the right, it's increasing. Okay. Well, folks, at this point, I feel a little concerned because we haven't even started section 2.9 yet, and there's a lot of good word problems on there. And so let's just click through here. The rest of these problems are essentially the same. So if you look at number 13, it says, here's a function, and this time they're asking you to find the inflection points. So they actually do want the inflection points this time. You would go straight to the second derivative, set it equal to 0, find the inflection points, and then tell what's happening over each part of those inflection points, telling you, is it concave up or concave down? So what's the first thing you could do to familiarize yourself with this problem? Look at the graph. And so that would be 12 x to the 5th plus 45 x to the 4th minus 80 x cubed plus 6. And so there's our graph. Yeah, I need to change my 30. Wow, that's still very wiggly. 100. Change my x. 10. Ah, there we go. Well, that's a little better. Wow, that thing goes really high up. I need to go up to 1,000. All right, so you can see the graph here, folks. It's kind of hard to tell because it goes, what is it first? What's its concavity? Concave down. But then it comes down here and there's something particular happening where it has an extra little wiggle down there. So how does its concavity change down here at the bottom? First it's concave up, but then it's concave down, and then it's concave up again. And that's what you would be finding as you do this test. Okay, we might do this one. Let me just click through here real quick to make sure that we've covered all the rest. Okay, I think this would be a fair one to do, and then we're going to move on to 2.9. So does everyone have this problem map in front of them? Let's go ahead and look at it. I'm going to erase all this. So we start off with our function, which we just took a peek at. So we know essentially that it looks like a polynomial graph. And it says that it had, it has those inflection points. Okay, so we need the second derivative. So our first derivative would be 60 x to the 4th plus 4 times 45, 180, x cubed minus 240 x squared. But we need to get our second derivative. And so that would be 240x cubed plus 180 times 3 is 450. X squared minus what? 480x. So we want to know, when is our second derivative equal to 0? Because that will be our inflection points. At an inflection point, what's your concavity? 0. Yeah, at the inflection point, the concavity is 0. So how do we solve this for 0? It's a cubic. We can't use the quadratic formula. What can we do to this expression? It's very unfortunate that it's a cubic because we can't do the quadratic formula to solve for x. But what could we do to this expression? Notice the numbers are quite big, and every term has an x. So what can we do? We can factor out a number and an x. What's the largest number we can factor out of 240, 450, and 480?
Probably more.
Definitely a 10. 60 goes into 60, 180, and 240, so we can take out a 60. I think 60 might be it. 60 might be the best. So let's everybody take out 60x. We take out 60x, that leaves behind 4x squared.
This 60x doesn't go into 450.
It's going to be 7.5.
Oh geez.
15.
Why does it not? Did I multiply that wrong? It's not 450, it's 480. Silly me, folks. I'm sorry, I made a typo. What do you call a typo if it's a calculation? A calculation-o? I made a typo, but with numbers. Yeah, that's 480. No, it's not. It's 440. What's 180 times 3? 180 times 3, that's 0. 3 times 3.
540.
540. Okay, massively different from anything I had written down. So it's 240, 540, and 480, and 60 does go into all of those. And so what does that leave us with? 9x and what? 8. Okay. Is that correct?
Yes.
It is correct? 240, 540, 40. Okay, that's correct. And we want to set that equal to 0. Now, I don't know if this is factorable. Does anybody think that's factorable? 32. No, it's not factorable. So you would have to use the quadratic formula. So on the one hand, you say, well, 60x could equal 0. And if that's the case, then x is 0. So that's one of our inflection points. But then we also have to solve this for x. So we say x is equal to the quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. And that gives us negative 9 plus or minus root 81. That doesn't look good. (16 times 8). Oh, but it's positive. So 81 plus 128 all over 8, which is negative 9 plus or minus the square root of 209 all over 8. Now right off the bat, that does look a little unfortunate because the square root of the 209 doesn't simplify. So we could always get a decimal approximation. I think that's not a terrible idea. If we did a decimal approximation, we have negative 9 plus or minus 14.5 all over 8. So we have two different values. .68 as one of our solutions, or negative 2.93. Okay, did you folks get the same results? You checking me as we go? So those are our three critical values. Those are our three inflection points. So if we went back to the graph, let's just take a look. If we go back to the graph, was there an inflection point at 0? It sure looks like it. That's concave up to the left and concave down on the right. Was there an inflection point at 1? No, that's not an inflection point. The inflection point would be around here, more than 0.5, yeah, 0.68. That looks like an inflection point. And our other inflection point was way over at -3. Let's just take a look. Yeah, that does look like where it would be. Because we were switching over from concave down to concave up, and that does look like it could be happening around -3. Okay, so those are our 3 inflection points. What do we do with them?
Well, first, for future purposes, but do we put them in like increasing order, like would D be
Yes.
-2.9?
Yes, thank you. Good question, Nate. So what I'm going to go ahead and do right now is make a number line where my values were -2.93, and then my next one was 0, and then my next one was 0.68. And those are the values of D, E, and F. Great question. So we now have our critical values in order. And it's asking us now for each of the following intervals, tell whether it's concave up or down. So since those are the inflection points where the concavity is changing, you would then, those are the inflection points when they're equal to 0, you'd have to find out what's happening to the right or left of it. So you'd have to, this is our second derivative, you would have to plug in test values to see what the concavity is in those other areas. Okay. To know what the concavity is like, first of all, the concavity at these 3 values is 0. Those are inflection points. So what's the concavity over here in this region? What's the concavity in this region? What's the concavity in this region? And what's the concavity in this region? What you do is you try test values. We've never done this in this class before. You try test values. So choose a value to the left of -2.93. Choose an easy one. -3. So you would try x equals -3. Choose a test value between 0 and -2.93. -1 would be great. So you try x equals -1. Let me write that up there. And then what's a good test value between 0 and 0.68? 0.5. Try x equals 0.5. And then what's a good test value to the right of 0.68? Yeah, 1. X equals 1. What do you get to do with those 4 numbers? Oh, that's -3. What do you get to do with them? Plug them into what? The second derivative, because that will tell you directly if it's concave up or down. So you would do all of that in your graphing calculator, in your calculator. So I'm going to go ahead and try that out. Here, I already have my function. Isn't that my function? Yeah, that's the original function. Oh, but I want the second derivative. Okay, so I'm going to type in the second derivative. So it'd be 240 something cubed, and then plus 540 something squared, and then minus 480 times something. So my first concavity value is negative. So already I know that this is negative concavity. I'm just going to put some minus signs there to show me. It's concave down. So then I plug in my next test value. So now my next test value was -1, I think, right? Yeah, I'm going to try -1. So I plug in -1, and I get a positive number. It equals 780. So now I know that we're concave up in this region. And then I try my next test value, which is 0.5. There we go. And that gives me a value of -75. So now I know I'm concave down. And then I try my next test value, which is 1. And that gives me a value of 300, which is also concave up. So what do we expect this graph to look like? Need a little room here. First, I would have my critical values. So here's my -2.93. Here's my 0. And here's my 0.68. And I need something that's concave down, then concave up, then concave down, then concave up. So I would draw something like concave down. Oops, that's the inflection point. Oh man. It would have to be concave down somewhere along in here, and then an inflection point to become concave up, and then an inflection point to be concave down, and then my next inflection point happens here to go concave up. Okay, that's a terrible graph compared to what we know it's supposed to look like, right? But does the graph actually do that? Oh, and I erased it all. Did the graph behave that way? Well, we're just going to check. 12x to the fifth plus 45x to the fourth minus 80x cubed plus 6. Did the graph do that? Let's just check. Did we start out concave down? Yeah, we did. And then we went concave up. And then we went concave down again. And then we went concave up. Okay, so that is how the graph behaved. Boy, I'm really glad we did that problem because we had never done that before with the whole trying of test values. And yet that is how you solve a problem like this. When they say, consider the function, find the inflection points, and then tell me over each interval, is it concave up or down? That's how you do it. And in fact, that feels a lot like the way we did the last problem, where the concavity turned out to be 0, and so we did the derivative to the right and left instead. That's also doing a test value. Okay, well, that's the end of the problem. You notice you don't have to find the actual maximum or minimum. They just want to know where the critical points are and whether it's concave up or down in between. So let me see here. 14 is the same way. 15 is the same way. And 16 is slightly different because it's asking about whether it's increasing or decreasing. Should we do one more? No, just move on. Okay. Because for 16, it'd be the same way. If they want to know in those intervals, is it increasing or decreasing, you would take a test value from each interval and just check the first derivative to see if it's increasing or decreasing. Okay, all right, well then let's keep going. So that was it for 2.8. In 2.9, we have a lot of applications. And
why I don't have 16?
what?
Why I don't have like 15, 16?
Why you don't have 15, 16?
Yeah, I end up with 14.
I don't know. Did a page get torn out? Do you guys have number 15 and 16? Yeah? Carmen, maybe you tore that page off and ate it.
Let me find it.
I don't know. All right. So this next section is a bunch of application problems that have to do both with cost, revenue, and profit, and a couple interesting ones about building a box. So what I'd like to do is actually not start with number 1 because number 1 is a little lengthy compared to some of the other ones, and I'd like to start with number 2. Can we all look at number 2 together? Should we take our break? We might as well. Okay, we might as well take a break. Let's take a break. And then when we come back, we're going to do number 2.
All right, I found it.
Oh, good, you did find it. Where was it?
Inside my binder.
Okay, Thomas is right here. Nate is here. Dave does not have one.
Yeah.
Of course you can. I thought you were asking if you could have a drink.
Oh.
Okay, this is your practice test, and then that's the actual test.
Awesome, thank you.
Where is Rose?
What?
Where is Rose?
That is a really good question. Is she not sitting right there?
No,
She's not there. Are you sure? She's under her blanket.
I don't know. But when the class started, like within 5 minutes, then she left.
Yeah, she was here, and then she left. I hope she's okay. I mean, someone would only miss math class if they were in real trouble. Asu, how was that?
But I actually did my homework ahead of the game, so.
Oh, so it made sense. Okay, good.
I watched all those videos.
Oh, good. And were they helpful?
Yes,
Well, good.
they were
Okay.
this time. Last, I think 2.7, they were a little
Well, you know,
different.
I should keep that in mind because, like, right now I'm feeling a little stressed because I want to cover all this material with you, But I should also make the assumption that your guys are watching the videos and reading the book. And if you're
Well, if I
watching
don't
the
get it
video,
on the first, I have to watch the little video and see how to get it.
you're what?
If I don't get it the first time, I watch the little video and
Ah.
see what I did wrong.
Okay, well, good. Oh, so in other words, you try the problem, and then you watch the video afterwards
If I didn't get it.
if you missed it. Yeah. Oh, that's a good plan.
Yeah, because sometimes they're like, 3, 4 minutes, 5 minutes long.
Oh, and you wouldn't want to watch that ahead of time. You're like, I don't want to watch the video if I don't have to.
Well, there's the easy ones, it just asks you if it's concave up or concave down. I don't want to watch the video.
Yeah, because that's pretty straightforward.
But where we had to substitute, I did because we hadn't done that in class. So I wasn't sure how to do it. I know one of them I was just like, whatever.
Yeah.
I watched the video 3 times and I just couldn't get it.
Okay, well, that makes sense. I'm reading a history of calculus book right now for a math course I'm taking next semester. Oh, it's really good. Yeah, anybody would love it. And so the other day I get to this particular chapter and I basically read 5 pages. And at the end of the 5 pages, I'm like, what? Like, I saw what they were doing, but it didn't make a lot of sense. So then I went back and I read it again last night, step by step by step, and did everything on paper. And at the end of it, I was like, that's easy. But the first time I read it, I was like, what? How do they do that? So it makes you wonder if sometimes your brain just needs multiple passes through an idea. Like the first exposure, you're like, ah, what? But then the second exposure, you're like, it's obvious.
But it also helps when you're writing it.
It helps when you do it
because now
yourself.
have a visual.
Yep. Yeah.
That's how I learn. I'm more of a visual, hands-on type person.
Mm-hmm.
That's just, you give me a book on my back.
Do you have to do it yourself? In fact, this particular book, the History of Calculus book, the very beginning they say, go get a piece of paper and a pencil because you have to do all these problems. And they say, we'll wait. And we'll say, and then they said, did you get a pencil yet? No, seriously, we'll wait. And then it went to the next paragraph. Seriously, did you get a pencil yet? We can't go on until you get a pencil. And then there were even a couple more times later on that page, they said, seriously, did you get a pencil yet? So they really were hammering the idea that you have to do all this yourself.
Well, our tax teacher forgot to give us our homework assignment.
Your what teacher?
Our tax.
Oh, okay. They forgot to give you your homework.
She forgot to post our homework online so we can move forward.
Oh, that's a bummer.
And so I went ahead and I just did my math homework.
Oh, well, good.
Because I knew I was going to get more homework anyways.
Yeah.
Did you get all your accounting done?
I did the first part. You know what? I'm sitting at a table. I have a table all to myself. And I just spread out all my books and computer and everything. And I probably sit about 3 hours a day. I hate accounting.
You hate accounting?
I hate it.
I'm so confused. Aren't you like studying to be an accountant?
I'm lining
No?
up a tutor for this week.
It's just, like right now we're doing the rates, and half of the rates you have to cut in half, and then the other one you actually have to use a full rate, and it's just like,
Yeah, my brain can't.
Are you guys all in the same accounting class?
we are.
But you're saying, ooh, you don't like it.
It's not nice.
Hmm.
At all.
Everybody, there's Rose. We were all wondering, Rose. We canceled class and we've just been waiting for you.
Awkward.
Yeah.
No,
talk
we-
about it.
So like we had to sign up for the transfer fair to volunteer, and I couldn't switch times, so I totally forgot about it. It was supposed to be 10 to 10:30.
So you went and volunteered.
Yeah.
Oh.
It was either that or run.
Run?
I would have had to run. Like coach doesn't like us missing things.
Oh.
Like when we make a word for it.
So instead of choosing to run or missing the fair, you chose to miss math class.
Yeah.
Okay, well.
I'm in already good shape. Like I don't need to run anymore.
Gotcha.
So.
All right, folks. Are we all back? Should we go ahead and get started again? Okay, so everybody, we're looking at number 2 on the packet that you just picked up today. Is that correct? This is the packet you just picked up today, and it's number 2. So turn the whole first page and go to number 2. Now, folks, this is a real problem. This is a real problem that manufacturers face all the time. And you might even start by asking yourself, why does cereal come in a cardboard box that looks like this, but oatmeal comes in a tube that looks like this? And why do cans of soup come in a cylinder that looks like this, whereas, you know, tuna comes in a cylinder that looks like this, and other food items come in boxes that look like this? What's the deal? Why is it, what's that? It could have to do with how you open them. Why is it that some manufacturers choose to go with the cylinder and some manufacturers choose to go with a rectangular prism? Nate?
They choose like what packaging best fits their product so they can use the least amount of material.
Yeah, I mean, that's the big one. They need it to fit the product appropriately. They don't want to damage the cereal or the soup or whatever's inside. But they don't want to spend a lot of extra money on material if they don't have to. They want to minimize material. And that's number 1. They want to minimize material, right? They don't want to use more material like a tin can or a cardboard box. They don't want to use more material than they have to because that's their cost function. But what do they want to maximize? Well, they want to maximize profit. They want to maximize the volume inside the container. So it's this really funny problem where they want to minimize the material, which means minimize the surface area. They want to minimize the surface area of the container because the surface area represents the actual material, like the cardboard or the tin. Whereas they want to maximize the volume inside the container because that's what actually contains the product that they're selling. You know, they're selling the soup or the tuna or the cereal. They're not selling the box itself. Everybody's just going to throw the box away and hopefully recycle it, or if not, throw it in a landfill. So we want to minimize the surface area but maximize the volume. And for some products, that turns out to be a cylinder, and for some projects, that turns out to be a rectangle. And it all depends on the product. So in this particular case, what are we saying in number 2? We're going to take a single piece of cardboard measuring 13 by 12 inches. So go ahead and just draw a single piece of cardboard, just flat cardboard, measuring 13 by 12 inches. And they're going to take that single piece of cardboard and they're going to turn it into an open top box by cutting squares with side length of X from each corner and then folding up the sides. So can you all imagine, like, you go to Mervyn's or a clothing store and you buy a nice shirt or something and they give you a box to put the clothes in and then you give the box to someone? Do you know what I'm talking about? They actually put clothing in boxes. You're like Mervyn's, there you go. Okay, I'm dating myself.
They're long gone.
They're long gone. Okay, Mervyn's or Kohl's or any clothing store. Have you ever bought clothes and they actually put it in a box? That's never happened to you?
Yes.
Thank you, Asu. Okay, well, there are actual boxes, and so it turns out it's like a gift box. It's just very thin, but it's a big rectangle. It looks like this, and it's just about yay tall, and you put some clothes in there. So anyway, what they do is they just cut a notch out of each corner, and the question is, how big of a notch should we make? So you're going to cut in X inches on all 4 corners, and then once you cut that little notch out, you can fold along here, fold along here, fold along here, fold along here, and then fold those 2 bits up and fold those 2 bits up, and then tape the edges, and then you have a box. So can you all imagine it? Actually cutting out the notches and then folding it up. What you end up with is something that looks like that. And then you have a box. And it would look like so. I mean, this is an amazing drawing, isn't it, folks? Yeah, so that's what you end up with. You have an open top box. And so now the real question is, if you're a manufacturer, what are you going to do with all those corners? You don't want to just throw them away or burn them. You want to do something with them, make a profit. So you come up with some other product that might actually use the little corners that you just cut out anyway. So we do that. Find a formula for the volume of the box. So what's the actual volume? What's the actual dimensions of my box now? It's no longer 13 by 12. what is it instead? How long is this width now?
It's 13 minus
2x.
x.
Yeah, 13 minus 2 x's, because you took away an x there and an x there, so it's 13 minus 2x. And then how long is this height here now? It'd be what? 12 minus 2x. So now the actual dimensions of our box, we've got 13 minus 2x for the length, and then 12 minus 2x for the width. And then how tall is the box? How tall is the box once you fold up the flaps? X. Okay, so does everyone feel comfortable about that model?
Yeah.
Again, as a manufacturer, this is a good way to make a box, but you'd still want to figure out what to do with those corner pieces so you're not just throwing them away. Maybe you turn them into confetti and start a confetti manufacturing business on the side. I don't know. So what is our volume? Volume is length times width times height. So we would say our volume is 13 minus 2x times 12 minus 2x times x. And that's our volume. Now, just in case you've never done a problem like this before, it's fascinating to note what this graph would actually look like. 13 minus 2x times 12 minus 2x times x. There we go. And this is what the volume curve looks like. What does that tell us? It means that as you make the notch x bigger, what happens to the volume of the box at first? The volume is increasing. Until there comes a critical point where if you continue to make that notch bigger and bigger, what happens to the volume of the box?
It decreases.
It decreases. Now, does that make sense? Why would the volume ever decrease as the notch increases? Yeah, there becomes a ridiculous point where you have actually notched out the actual whole box. You've actually taken out the whole, you took out that notch, and you took out that notch, and that notch, and that notch. And at that point, you actually just have a piece of cardboard that doesn't even fold up into a box anymore, and the volume is 0. So there comes a point where you cut out a notch that's too big. And so what's the balancing point? Well, we want to find this critical point right up here, which apparently I can already tell the answer is 2.078. So if you want to write that down, you can. Apparently, the best size of the notch, wait, sorry. Yeah, that's the volume, is if the notch is 2.078, and then what's the volume of the box? 144.156. So I'm going to go ahead and make a note that apparently x should be 2.078, and the maximum volume of the box would be 144.156. Now again, what I just did was cheating. I just looked at the graph. Right? I just looked at the graph. So we didn't actually do the work the way we're quote unquote supposed to. We need to use calculus and build an argument. So what do we do first? We want to take the derivative of volume, how volume is changing, and then set that equal to 0. We want to do the first derivative because that's going to tell us the critical point of the maximum of the curve, right? Because this volume curve is just another curve like anything else. We want to take the derivative, set it equal to 0, and find our critical point. So should we take the derivative of this? That's a triple product. Have we ever done the product rule on a triple product? No. What would we be better off doing? We'd probably be better off foiling, folks. So 13 times 12 is 156, and then minus 26x minus 24x plus 4x squared times x. And so that's going to be 156 minus 50x plus 4x squared all times x. And so it's 4x cubed minus 50x squared plus 156x. That's our volume. Now it's just a polynomial, and we can take the derivative using the power rule, much easier. So we take the derivative, and if this is v of x, we're going to write v prime of x now. And so that'll be 12x squared minus 100x plus 156. And we have to set that equal to 0. Can we factor anything out? We can can definitely factor out a 2, maybe even a 4. Might as well factor out a 4. So we take out a 4, that's 3x squared minus 25x plus what? How many times does 4 go into 156?
18?
39.
39, great. So we divide off the 4 cancels out, and we have to, I don't think that that factors, so we would have to use the quadratic formula. So the quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c, whatever 4 times 3 times 39, whoa, 4 times 3 times, I got 468 all over 2a, and a was 3, so that's 6, and then minus. That gives us 25 plus or minus the square root of 157 all over 6, and that's going to give us 2 possibilities, right? What is the square root of 157? 12. So 25 plus or minus 12.53 all over 6. So we'd have 25 plus 12.53 divided by 6. One possibility is 6.255. Or you have,
I have the other one at 22.91. Or it has to be negative, right?
it doesn't have to be negative.
22.91.
I got 2.078, which is good because that's the answer we got earlier by looking at the graph. So double check your quadratic formula. You should have ended up with the 2.078 and the 6.255. And the 6.255 actually doesn't even make sense as an answer. Why does that choice not even make sense as an answer? Look how wide the original box is. 12. Can you cut out a notch that's 6.2 inches wide in both directions? No, because 6.2 times 2 is 12.4. That's larger than the original box. So this answer choice is extraneous. It does not make sense. And therefore, the actual value that is true is 2.078. And that agrees with what we did. That agrees with what the graph showed us. So the maximum volume is at 2.078. And so then how do we actually get the volume? What do we plug our 2.078 into? Yeah, in the actual volume formula. The actual volume formula. So the actual volume, given that the notch is 2.078, would be 13 minus 2 times 2.078 times 12 minus 2 times 2.078 times 2.078. And if you calculate that, that should give us the maximum volume that the graph gave us. Which I'm sure it does. 2 times 2. And 12 minus 2 times 2. Yeah, I got 144.155. Okay, so that's it. So again, if you're the manufacturer and you have these, somehow you have a whole bunch of sheets of cardboard that are 13 by 12, and you want to build a box that holds the most volume, then that would be your choice, is to cut a notch that's 2.078. And so what would your final, the actual dimensions of your box be? The height would be 2.078, and then you'd calculate the width and then the length, and that would be your box. Folks, on the test, or on any test in calculus, by all means, you can use your graphing calculator. You can use your graphing calculator to graph this graph and use that to confirm your answer, okay? But you still have to show me the work, the calculus, to show me where you got the answer. So on the test, by all means, graph it if you want to, but make sure you're showing me the actual work to show me where the 2.078 came from. Because if you just tell me that it's 2.078, but you don't show me any work, then I can't give you full credit. Okay, how did that problem feel? Okay, we're gonna continue to skip number 1 for now. Let's move on to number 3. Whoa, number 3, this is an exciting one. This might feel a little arbitrary. Number 3. Please go ahead and read it. Tell me what's even happening. Read number 3. What does this even look like? A rectangle is inscribed with its base on the x-axis and its upper corners on the parabola y equals 12 minus x squared. So draw a graph, and apparently the rectangle is sitting on the x-axis, but its upper corners are on the parabola y equals 12 minus x squared. Well, here's 12 minus x squared. I have to fix my window. There we go. So now does this make sense what's happening? We've got our parabola here. Oh, that was terrible. We have our parabola, and a rectangle is sitting on the x-axis, and where are its upper corners? Touching the parabola. So is this an acceptable interpretation of the problem? Does that make sense? Okay, so that's what they're asking us to do. They want us to build a rectangle with its base on the x-axis and its upper corners on the parabola. What are the dimensions of such a rectangle with the greatest possible area? So just for kicks, the first thing I'd like you to do is draw this, and then draw lots of different possible rectangles. Like for instance, couldn't it look like that? Or it could 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 look like this? Or it could look like that? And so you have lots of different possible rectangles. You've got a rectangle that's tall and skinny. You've got a rectangle that's wide and short. And you've got even a square. Isn't there a square in there somewhere? Yeah. Somewhere in there, there's a square. Because I went from a wide rectangle to a skinny rectangle, so somewhere in there, there's actually a square. That could be a problem in and of itself, is where's the square? What are the dimensions of the square that fits inside? But what question are they asking? They just want to know the greatest possible area. Now, ironically, what kind of rectangle has the greatest possible area? A square. Yeah, so actually we're solving both problems simultaneously. If you look at all the different ways that you can make a rectangle, a square is always going to have the maximum area given fixed perimeter. So if you only have so much fencing to enclose an area, then you'd want to use your fencing to enclose a square because the square will have the most area inside, like for pigs or horses or whatever. If you want to build a pen, then you want to make it into a square because it maximizes area. Okay, well, let's go ahead and solve the problem. How do we do it? You have your parabola, just draw a rectangle. We know that this parabola is f of x equals 12 minus x squared. And we have our rectangle. So what do we need to know about a rectangle in order to calculate its area? Area equals base times height. What is the base? How wide is it? Since this is 0, what's this point right here? What should we call it? We could just call that x, right? And therefore, this over here is negative x, and how wide is the rectangle? If it's x to the right and x to the left, how wide is it?
X squared.
Not x squared, 2x. So the whole width is 2x. And convince yourself that you agree. So Rose, what's 1x plus 1x?
Who else?
Yeah. Okay, so we know that that's how wide our thing is, but how tall is this rectangle now? How tall is it? The y value, right? That's what the function tells us after all. The y value, the function tells you the y coordinate, which is the height. So the actual height right there is what? 12 minus x squared. So that's your height, and therefore that's how tall the box is. The box is 12 minus x squared tall, because the function tells you the y coordinate, and the y coordinate is the height, and therefore the height is simply 12 minus x squared. So once you choose a particular x value to build your rectangle to the left, I'm sorry, to the right and left, then you automatically know how tall the rectangle is. And so our base is 2x, our height is 12 minus x squared, and the formula for area is 2x times 12 minus x squared. What should we do to that? Since we're about to take the derivative. Yeah, we should FOIL it, or in this case, just distribute it. It's not really FOIL, it's just full. Right, isn't it just first, last? It's just full. So we distribute, and we get that the area formula in terms of x is what? 24x minus 2x cubed. So then we go ahead and take the derivative of area. Because again, just like before, if we were to graph this on our graph, you would see the area getting bigger and then smaller. So the area, the first derivative is 24 minus 6x squared. And we want to find our critical point, so we set that equal to 0. And this is a refreshingly simple one to solve. We could go ahead and move the 6x squared to the other side, so it's 24 equals 6x squared. Divide off the 6, and we get x squared is equal to 4, and therefore x is equal to 2. Plus or minus 2. And interestingly, both of those answers make sense, because if the width is 2, we're talking about this corner. If the width is -2, we're talking about that corner. But we're still talking about the same rectangle. If the x value is 2, how wide is our actual rectangle? Since 4. So the actual width is 4. How tall is our rectangle since x is 2? 12 minus x squared, 12 minus 2 squared, 12 minus 4 is 8. So the actual rectangle is 8 by 4. And oh, that's so strange because that actually is not a square. So it would be really interesting to find out what the square would be that fits in there, and the fact that that does not actually maximize it. And it's because we fit it inside of a parabola. Now, earlier I told you that in order to maximize the area, it would be a square. That's if you have fixed perimeter. Again, like you only have so much fencing to build a pen of some sort, you would want to build a square. But in this case, this is the maximum area. How could we check that to be more confident? We could graph it. So is it 12 minus x squared times 2x? So now here's our graph. You can tell it's not exactly a symmetric parabola, but the maximum is indeed up at 2. And what's the maximum area up at 2? 32. Isn't it amazing that you could have done this whole problem like that by just graphing it and looking at the maximum point? That's why graphing calculators are so powerful, because they immediately tell you the answer. But this is the actual machinery, the mechanics, the calculus behind it. Okay. So when would it have been a square? When would that shape be a square? Wouldn't it be a square when the width and the height are equal to each other? So we'd have to find out when is 2x equal to 12 minus x squared? When is the width equal to the height? When is that? If I bring the x squared over, it's x squared plus 2x minus 12 equals 0. Can you factor that? 4 times 3, 6 times 2? No, I don't think it's factorable. When is that equal to 0? Oh, how strange. Well, okay, never mind. It doesn't matter. We don't need to solve it, so let's keep going. That's it. I would expect you to be able to solve one of those two types of problems on the test by model. So the next few problems, 4 through the rest, 4 through 14, these are all business problems. Business problems, which, you know, those are the important ones, because that's what this class is all about. It's how do we apply calculus to solving questions about profit and cost and revenue and all that. So I think let's just go ahead and start working through them. Everybody on number 4? It says the given cost function is 28,000. I'm going to go and write it down. So this is number 4. The given cost function is 28,900. What does that represent, by the way, the 28,900? There's no variable on that. What kind of cost is that?
Fixed.
That's your fixed cost. Yeah, like you're done. You already invested $28,000. And then the 800x and the x squared, that's your variable cost, depending on how many actual units you make. So what's the cost of production level 1300? We're not going to solve all of these together because some of this is simple for you to do on your own. How do I find the cost at 1300? So x is the number of units that you're making. So how do we find out? What do you want? How do I find out the cost if I make 1300 units?
Just plug in.
Just plug it in. Yeah, you're just going to plug in 1300 into your cost function. I mean, that's how a cost function works. It's telling you the cost depending on how many units you make. So again, that 28,900 was your fixed cost. You have to pay that no matter what. But depending on what you plug in for x, that's telling you your variable costs. And so your cost for 1300 units would be just plugging in the 1300 for x. All right, and I'm not going to finish calculating that, but that's just how you would do it. You just plug it into the cost function. Well, what's the average cost? They mentioned this in the book many chapters ago. How do you calculate average cost, folks? What does that even mean, average cost? Because this is telling you the cost for all 1300 units. You do what? You don't have to take the derivative to get the average. How do you get any average, folks? Like, what if you had 3 test scores and you wanted to average them?
Divide by
You'd add them all together and divide by 3. And so here we have 1,300 products. This is the cost for all of them. So I just added up the cost of all 1,300 items. And then what would I do to find the average? Divide by 1,300. So the average cost, you might want to write this down, the average cost would be C of x divided by x. That's your average cost. That's the formula. So again, you might want to write that down first. The average cost is you take your cost and divide it by how many items you just made. In this case, it's going to be C of 1,300 divided by 1,300. And what you're really doing there is you're splitting this cost up amongst all 1,300 items. And so instead of thinking about one big fixed cost of 28,900, you just divided 28,900 by 1,300 to say, well, you know, my fixed cost per item wasn't that bad. My fixed cost per item was 28,900 divided by 1,300. My fixed cost per item, if you actually do it, folks, it's interesting to note, 28,900 divided by 1,300 is only a fixed cost of $22.23 per item. So your fixed cost doesn't feel too bad anymore. You think, oh my gosh, I just invested $28,900. But your only fixed cost was $22 per item that you made. Okay, so anyway, that's your average cost. What about the marginal cost? What is that word marginal again? It means you have to, what? Yeah, take the derivative. Marginal cost is the derivative. So marginal cost, let's remind ourselves, marginal cost is, well, there's 2 different ways to write it. One of them is the derivative of cost. It's the first derivative of cost. But what's the actual? They say the marginal cost at production level of 1,300. So we're going to take the first derivative and plug in 1,300. But if you actually wanted to know how much it cost you to make the 1,300th item, how else would you compute it? What's the traditional pre-calculus way? Well, you want to know the cost of the 1,300th item. That would tell you the cost of the 1,301st item. So what would it be? Yeah, the cost of the 1,300th item minus the cost of the 1,299th item, that would be the traditional accurate, correct cost of the 1,300th item. You would take the cost of all 1,300 items, subtract the cost of the first 1,299 items, and that would tell you the actual cost of the 1,300th item. So that's the traditional way, cost of the 1,300th item. But using calculus, we come up with this fairly good approximation. So remember, this is a fairly good approximation. Ironically, the calculus approach is not the best answer because it's just an approximation. Okay, well, again, I'm not actually doing these with you. I'm just talking about it. You can certainly go back and do these calculations. They're all fairly simple. So that would be your marginal cost. What about D, the production level that will minimize the average cost? What if we wanted to minimize the average cost? What? Well, first of all, this is the average cost, right? So let's go ahead and write down what the average cost formula is. What's the formula for average cost? You take the whole thing and divide it by x, right? So that would be 28,900 plus 800x plus x squared all over x. And since that's the average cost, and now I want to minimize it, how do you find a minimum? How do you find a minimum? Yeah, you take the first derivative and set it equal to 0. Now, how do you want to take the first derivative of this? Do you want to do the quotient rule and do ho-de hi minus hi ho over ho-ho? Or do you want to go ahead and divide each term over x? Because that might be easier. It might be easier to look at this as 28,900 over x plus 800x over x, which is just 800, plus x squared over x, which is just x. Does anybody like that better?
What would we do then there?
Well, now you take the derivative of each term. And I think this is actually better. So I'm going to do some erasing so that I can actually do this one with you. I'm going to do this one with you. So I hope everybody has all that down. I'm going to erase all this business and start with that. So part D, we'd like to minimize average cost. And my formula for average cost is 28,900 over x plus 800 plus x. Now, of course, can I actually take the derivative of 28,900 over x? I have to rewrite that how? Yeah, x to the negative 1. So that's really 28,900 x to the negative 1 plus 800 plus x. And I'd like to go ahead and take the derivative of that. So that would be negative 28,900 x to the negative 2 plus the derivative of 800 is nothing, plus the derivative of 1x is 1. So look at that. That's actually our first derivative. What should we call that? AVG prime of x? Is that acceptable if we just go ahead and call that AVG prime? We don't really have an agreed upon way of writing that, so I'm just going to write average prime. So that's the first derivative of average cost, and we want to find out when that equals 0. Now, right now I'm going to go ahead and change this x to the negative 2 back to the denominator, because that will make it easier for us to do our computation. So I'm going to go ahead and change this to negative 28,900 over x squared plus 1 equals 0. And how do I solve that for 0? Yeah, we want to go ahead and move this term over to the right-hand side so that it's positive. I mean, you could move the 1 over if you like, but I'm going to move the whole term over. So I have 1 equals 28,900 over x squared. And then how do I get the x by itself? It's trapped in the denominator right now. Do what? Yeah, multiply the x squared over to the other side. That way it cancels it from the denominator. And we have x squared equals 28,900. And oh my gosh, how exciting. You can actually take the square root of 28,900. And what is it? 170. What does that tell us? What problem were we just solving? The production level that will minimize the average cost. We wanted to make the average cost as small as possible. So how many products should we sell? 170. And then part E is just saying, and what was that average cost? So how do we find the actual average cost? Do we plug 170 into the derivative of average cost? No. We plug it into the actual average cost formula. So the actual average cost formula, I'm going to go back to average of x. That was 28,900 plus 800x plus x squared all over x. That was my actual average cost formula, right? And we'll plug 170 into that. So the average cost at 170 would be that. And of course, you would type all that into a calculator. Did anyone check me that the square root of 20,900 really is 170? Did anyone check me? Oh my gosh, it is 170. Okay, and then you plug it in, 28,900 plus 800 times 170 plus 170 squared, all divided by 170. What did you all get?
190,000.
Did you divide that by x to get the average yet? Okay. I believe I got the average cost to be 1,140. What did anyone else get?
That's the same thing.
You got the same thing, Nick? Nick, are you just telling me that, or you really did? All right, thanks, Nick. All right, so there we go. That's one good solid problem that you can definitely expect to see not only on this upcoming test, but also on your final exam. Because that's classic. Yeah, Mom.
And how do you do for 800? Like number 2,
Where?
800?
What's the derivative of 800?
Yeah.
What is the derivative of 800? What's the derivative of a number? 0. The derivative of 1x is 1. The derivative of this was this. The derivative of 800 was nothing. Remember, the derivative of a constant is just 0. Yeah. Okay. Folks, how'd you feel about that problem? That's a pretty standard problem. That's an incredibly standard problem to talk about. All right. And number 5, what's different about this number 5? First of all, are the questions the same? What's the cost at the production level? What's the average cost? What's the marginal cost? What's the production level that will minimize? And then what's the actual minimum average cost? Are they the exact same questions?
Yeah.
Yeah, they sure. What's the difference?
The square root.
Yeah, the square root and the function's a little different. But at any point in this problem, did we ever take the second derivative? No, so all we have to really deal with is the first derivative. So I don't mind at all. Let's just go ahead and look at the derivative of this thing. Did we actually take the first derivative of the average of the cost function? Or the, oh, actually we did, didn't we? We had to find marginal cost, and that was the first derivative of the cost function. But then we wanted to find the minimum of the average cost, so we had to take the derivative of the average cost. So don't we have to take the derivative of both? I'm going to start by writing out my cost function, which is 54 root x plus x squared over 1,000. But then also, here's our average cost function, which I'm just going to write AVG, if that works for everybody else. I suppose we could write it AC for average cost, but I kind of like AVG. What do you all want to do? Is that fine? Okay. So now the average cost would be all that over x. So we have our cost function and our average cost function. We do have to find the derivative of cost because they're asking us to find the marginal cost. So that's the derivative of cost. And we also have to find the derivative of the average cost function because that's the the minimum of the average cost. So we have to do both. So how do we take the derivative of this one? You just have to rewrite it as 54x to the 1/2, right? And that's x squared over 1,000, which you could also call 1,000 x squared if you wanted to. So that would be pretty straightforward to take that derivative. We can still do it though. I'm happy to still do it. Whereas this problem, you would have to rewrite this as 54x to the 1/2 plus 1/1000 x squared. And both of those are going to get divided by x. How does that simplify out? How do you simplify this first part, x to the 1/2 over x? What is it?
Would it be 54 over x 1/2?
Yeah, it would be 54 over x to the 1/2 because you have, this is really x to the 2/2 down here. And so it would be 54 over x to the 1/2, or what else could you say? Because we're about to take the derivative of it. 54x to the negative 1/2, and then this one is simply 1/1000 x, because one of those x's canceled out. Now, in the cost case, we're finding the marginal cost. All you have to do is take the derivative. So that derivative is pretty easy. Half of 54 is 27x to the negative a half plus 2 1,000ths x. So that's the derivative of cost. Do we have to set that equal to 0? Are they asking us to find the minimum cost? What are they asking us to do?
Or not there.
They just want the marginal cost at the level of 1,300. So do we have to set this derivative equal to 0? No. All we have to do is plug in 1,300. So we plug in the 1,300, and that will tell us the marginal cost at 1,300. So that's one of your answers. The marginal cost at 1,300. Will this answer be accurate? No, it's an approximation. This answer is merely an approximation to the real marginal cost of the 13th approximation. Yeah. Okay, so then how do we take this derivative? Well, you still just do the power rule. So you bring down the negative 1/2, that's negative 27x to the negative 3/2 plus 1 1,000th, and that's it. So that's the derivative of the average cost. Now, do we set this equal to 0?
No.
Yeah, because they were asking us to find the production level that will minimize the average cost. So to find the minimum, you have to find the critical point. So you take the derivative, and then you set it equal to 0. So I'll finish this one with you. We still have a minute or two, I think. If we set this equal to 0, then we go ahead, and I'm going to move my negative term to the other side. So I have 1 1,000 equals 27x to the negative 3/2. Ooh, this looks a little gross, doesn't it? And I want to solve for x, so I'm going to divide off the 27. So I'm going to multiply both sides times 1/27. That way those 27s cancel, and I have 1 over 27,000 equals x to the negative 3/2. Folks, how do I solve for x right now?
Just put it to
You could do a couple different things. You could put it 1 over x to the 3/2, and then that's actually 1 over the square root of x cubed, right? So you could go all the way back to there, and then you could, oh man, then you'd have to bring the square root of the x cubed up back over to here to get it out of the denominator, and then you'd have to solve for x, right? Well, I'd like to recommend a different possibility. Right now, x is being raised to the negative 3/2. What do we want to get? X to the power of 1, right?
Yeah.
So when you raise something to a power, you multiply the powers. So what exponent could I raise this to such that negative 3/2 times what would equal 1? Just 2/3? Negative 2/3. If I raise both sides to the negative 2/3, this is a clever trick. If I raise both sides to the negative 2/3, well, now these powers multiply, and I get 1, and I just solve for x in one step. Over here, I now have to compute 1 over 27,000 to the power of negative 2/3, which, how can you do that? On your calculator. You can just type in 1 over 27,000 to the power of negative 2/3. Everybody on your own calculator, go ahead and try that. Let's all make sure that we're all using our calculators correctly and that you know how to type that in. If you type in parenthesis 1 divided by 27,000 to the power of negative 3/2, dude, what did you get? Oh, negative 2/3, not negative 3/2, negative 2/3. Yeah, what'd you get?
2, 4, 3 was 1, 2.
I didn't get that. Everyone try 1 over 27,000 to the power of negative 2/3. What did you get?
I trust you.
I'm not going to write it down until I hear somebody say it. Your calculator should be able to do this. And I would use a lot of parentheses, folks. You want to use a lot of parentheses. You would type in parenthesis 1 divided by 27,000. Parenthesis, caret, parenthesis, negative 2/3. What did you get? I got a really nice even number.
1.
No, not 1.
2.
Everyone, did it work?
900.
900 is the answer. It was nice and simple, 900. Everybody, I really encourage, this would have been a great time to try this on your calculator, see if it works, and then let me know if it didn't, so I can show you. Who'd like to see how to type it in? Did it work? You got it? Okay, well, if you want to ask me, you can ask me after class. And I guess class is over. Yeah, I guess it is. Folks, we didn't finish section 2.9 because we're wrapping up 2.8. So when I see you next time, actually, a lot of these problems will be similar. But we will go back to this on Thursday. Because I do want to go through those. And then when we do section 210, oh yeah, 210 is pretty short. Okay, we'll be able to do this.
Or skip the 210.
No, 210 is a really good one. It's incredibly short. There's only 7 problems and they're mostly duplicates. So we're still good. We can do this on Thursday.
Bye.
Bye, Carmen.